Chapter 1.10.2 Assigning Pods to Nodes. Here is a short summary about the article. Pods can be assigned to nodes using label selectors to limit or prefer specific nodes, enabling better resource allocation and availability. Node selectors, affinities, and anti-affinities allow more expressive control over pod placement, ensuring optimal performance and resource allocation. Restrictions like node isolation, node taints, and pod topology spread constraints enhance pod scheduling capabilities. Okay, that was the short summary. Let's have a deeper look into the contents. Assigning pods to nodes. In Kubernetes, you can control pod placement using several methods such as label selectors, node selector fields, and affinity settings. This allows you to restrict pods to specific nodes, ensuring appropriate resources, like SSDs, or optimizing for communication-heavy services within the same availability zone. Although the scheduler typically handles satisfactory placement, these options provide more precise control when necessary. Use node name and topology constraints for further customization. Node labels. Kubernetes nodes come with labels that can be manually attached or automatically populated by Kubernetes with a standard set. These standard labels have values that can vary depending on the cloud provider, making them potentially unreliable for certain uses. For instance, the kubernetes.io/hostname label might match the node name in some environments but differ in others. Node labels are utilized to target pods for specific scheduling based on isolation, security, or regulatory requirements. To ensure protection, labels for isolation should have keys that the kubelet can't modify, preventing compromised nodes from abusing the scheduler. Enabling the node restriction admission plugin and adding labels with the node-restriction.kubernetes.io/prefix secures node isolation. Utilizing labels like example.com.node-restriction.kubernetes.io/fips equals true. Node selector. The node selector field in Kubernetes is a basic method to set constraints for node selection. It allows you to specify node labels in your pod configuration, ensuring that only nodes with those specific labels are chosen for the pod's deployment. This feature is detailed further in the Assign Pods to Nodes documentation. Affinity and anti-affinity. Node selector ** provides a basic method for aligning pods with nodes that have specific labels. While effective, it limits the condition to only nodes with all listed labels. Affinity and anti-affinity * enhance node selector's functionality by allowing more detailed control over node selection. Language, more expressive than node selector. Rules can be marked as soft, preferred so pods still schedule even without a match. Pod labels allows rules based on labels of neighboring pods, enabling co-location rules. Node affinity * functions similarly to node selector but offers a more expressive syntax. Required versus preferred. Define whether rules are hard, must meet, or soft, preferred but not essential. Operators provides a flexible set of logical operators for rule definition, enabling sophisticated selection logic. Affinity weighting * allows prioritizing nodes through a scoring system. Weight is applied to preferred rules, with consistent nodes scoring higher. Useful examples include zone-specific labels to increase node scoring. Interpod affinity and anti-affinity * define constraints based on existing pod labels on nodes, rather than just node labels. Control co-location effectively, ensuring related workloads are placed together or apart. Require consistent node labeling, risking inefficiencies if labels are missing. In large clusters, the processing demands may impact scheduling performance. Practical applications *. Interpod affinity and anti-affinity effectively pair with replica sets, stateful sets, and deployments. Examples include minimizing latency by co-locating related applications, web apps, and services, caches. Anti-Affinity supports spreading workloads for redundancy and high availability, as seen in the Zookeeper tutorial. Code example. The code defines a pod named with node affinity specified. The pod is required to be scheduled on nodes with the labels topology.kubernetes.io/zone set to either Antarctica East 1 or Antarctica West 1, and it is preferred to be scheduled on nodes with the label another node label key set to another node label value with a weight of 1. The pod contains a container named with node affinity using the image registry.k8s.io/pos:2.0. This code defines a pod with node affinity, where it prefers to be scheduled on nodes with label 1 and label2, with weights of 1 and 50 respectively. The pod requires nodes to have the label kubernetes.io/os set to Linux for scheduling, but it prefers nodes with label 1 or label 2 based on their weights. The containers section specifies the container to run in the pod. This code configures a Kubernetes scheduler configuration with 2 profiles, one for the default scheduler and one for a scheduler named foo scheduler. The foo scheduler profile specifies plugin configuration for node affinity with added affinity that requires nodes to have the scheduler profile key with a value of foo for scheduling. This setting ensures that pods with spec scheduler name set to foo scheduler will only be scheduled on nodes that have the specified label. This code defines a pod with pod affinity and pod anti-affinity rules. The pod affinity rule requires the pod to be scheduled on a node in a specific zone where other pods have the label security equals S1. The pod anti-affinity rule prefers to avoid scheduling the pod on a node in a specific zone where other pods have the label security equals S2, with a weight of 100 assigned to this preference. This code defines a deployment for an application server with pod affinity rules. It specifies that the pods from the same rollout with the label app database should be scheduled in the same zone topology. Additionally, it includes a match label keys field with the value pod template hash to target pods belonging to the same revision for better affinity management during rolling upgrades. This code snippet defines pod affinity and anti-affinity rules to ensure that pods associated with the tenant label are scheduled onto the correct node pool based on the node pool topology key. It also prevents pods from the tenant label from being scheduled onto nodes where pods from a different tenant are running, using the mismatch label keys field and a label selector to only select pods with the tenant label for comparison. This code defines a deployment for a Redis cache with 3 replicas. The pod anti-affinity rule in the "spec" section ensures that multiple cache replicas with the label "app equals store" are not placed on the same node, using the kubernetes.io/hostname as the topology key. The container section specifies a container named Redis server using the Redis 3.2 Alpine image. This code snippet defines a Kubernetes deployment called web server with 3 replicas. It specifies pod anti-affinity rules to prevent multiple instances of the web app in the web store app label from being scheduled on the same node, and pod affinity rules to ensure that web app instances are scheduled on nodes where pods with the store label are running. The containers in the deployment run the Nginx 1.16 Alpine image for the web application. Node name. The node name field in a pod's spec offers a direct method for node selection, allowing a pod to be scheduled on a specific node. This overrides nodeselector and affinity rules. Unlike nodeselector, if the designated node name isn't available, the pod won't run, possibly being deleted if unavailable. Also, insufficient resources on the specific node will prevent the pod from running due to errors like out of memory. Furthermore, relying on node names can be problematic in cloud environments where these names might change unexpectedly. Node name is recommended for advanced use cases or custom schedulers needing to circumvent standard scheduling rules. However, it's risky as pods may fail if nodes become oversubscribed. To avoid such issues while still specifying nodes, one can use node affinity or NodeSelector without bypassing default schedulers. Example pod spec using node name assigns pod to node Cube01 exclusively. Code example. This code defines a pod resource named Nginx with a single container running the Nginx image. The pod is specified to only run on the node named Cube01 by using the node name field in the pod spec. This means that the scheduler will try to place this pod specifically on the node Cube01 without considering other nodes. Pod topology spread constraints. Topology spread constraints in Kubernetes enable controlling the distribution of pods across various cluster domains, e.g., regions, zones, nodes. This strategy aims to enhance performance, availability, or resource utilization. For detailed information on implementing these constraints, consult the pod topology spread constraints documentation. Operators. In Kubernetes, logical operators like node affinity and pod affinity are used to guide the scheduling of pods. Within this context, operators such as GT, greater than, and lieutenant, less than, are specific to node affinity conditions, requiring integer values. If the value cannot be interpreted as an integer, the pod scheduling will fail. These operators are inapplicable for pod affinity, emphasizing their tailored usage for node affinity alone.